This recording will cover Chapter 5, which is about fitting data to curves. What we're going to talk about here is taking an independent and dependent variables that have a relationship with one another, but that relationship isn't necessarily linear. It actually follows a curve type relationship, so increasing at an increasing rate, increasing at a decreasing rate, and so on and so forth. And what we're going to do is we're going to talk about how to transform that data into data that will have a linear relationship so that we can analyze it using a linear regression. So the linear transformations we're going to discuss are polynomial regressions. We'll focus basically just on quadratic and cubic, so x squared and x to the third, but you can go farther than that if necessary. Then reciprocal transformations, which is 1 over x, or the inverse of x, where x is any independent variable. And then finally, logarithmic transformations. We'll discuss 3 varieties here. Transforming just your independent variable, transforming just your dependent variable, or transforming both. So how do I know which one I need to do? Your first step is always going to be to graph your independent variables against your dependent variable. Now remember, when you do this in Excel, you have to have x, then y, and in that specific order. So the first column has to be x's, the second column has to be your y's, in order to go through and do that scatter plot. With SPSS, it doesn't matter. You just select, which is your independent, which are your dependents, in order to go through and do that. So if you have multiple independent variables, you're going to need multiple scatter plots. So one for each independent variable. And you're going to try to see if you see any curvilinear relationship. And we'll talk about how to spot the relationships. And the second thing you're going to do is examine the residual graphs. So if you see a pattern in the residuals, then that's a problem. So residuals are your errors, your misses. You want any kind of miss to be completely random. You don't want to see any sort of pattern in your errors. So the first example we're going to talk about is polynomial regression. It's a common correction for nonlinearity is to add powers to the explanatory variable. So if we decide we need the term x squared, then we would always have to remember to include the lower order term, just x, even if that x by itself is no longer significant. So the way we discuss these, the order of the regression is called the highest power. So this would be a k-powered regression. So this would be, we have beta 0 as our intercept, beta 1 is the slope coefficient of the first ordered term, which is x to the first. Beta 2 is the slope coefficient of the second ordered term, which is x squared, and so on and so forth, and this can go all the way up to k. So if we have x squared, we need to include both x and x squared. If we have x squared, and x to the third, we need to include all of them in there. So don't just include the squared or the third terms. Remember to always include any of the lower ordered terms in your regression as well. So how do I know which I should be doing? Well, we have our general looks. If you see, if we see this type of relationship increasing, we have decreasing at an increasing rate and then increasing at an increasing rate. So the parabolic relationship from either side, or or that being flipped upside down, that would indicate a quadratic, versus that S-shaped kind of relationship would indicate a cubic or a third order type regression. So the first thing we're going to do is go through and actually plot this. And what we see here, we're doing this example, Telemarks 5 is the data set. We have information on 20 telemarketing employees, the average number of calls per day they've made over the last 20 work days, and the number of months they've been on the job. And we see that as the number of months that they've been on the job increases, the number of calls they make also increases, but at a decreasing rate over time. So it's kind of like they're gaining experience, they're able to make more calls and more calls and more calls, but they can't just keep infinitely increasing. They're increasing in number of calls tends to decrease. That rate of increase tends to decrease over time. So we see increasing at a decreasing rate. And the first step for all of these, so just for comparison purposes, after we've done our scatter plots to determine what type of transformation we need to do, the first step in order to see was our transformation correct is going to be to run your linear regression. So here I have the linear regression run in Excel. We have the R squared is 87%, so the number of, roughly 87% of the number of calls per month is explained by the number of months they've been on the job. We have our coefficient 0.74, so for each additional month on the job, the number of calls per workday is predicted to increase by 0.74. Okay, and we see, looking at that p-value, that months is statistically significant, and by the p-value of the f statistic also is confirming that, since in this case there's only one independent variable. So our t-test with an HO of beta months equals 0 is the same as our f-test. And then we can move on in Excel to do the second order term, or second order model. So here now we've created a new variable, months squared. So in order to create that, I just, actually literally went in and created a new variable. So months, I made a new column, months squared, and then, you click on there, you click on the months term, you square that term, and there you go, there's months squared. So we want to look at this model, and we're going to say, okay, well, is months squared statistically significant? Yes, I see that it is. Now be really careful, because you can't, the interpreting months squared gets a little more complicated. Don't just say for each additional months squared they're on the job. No, that doesn't make any sense. Also, be really careful about using this model to make predictions. So if you need to use this to make a prediction and say the employee's been on the job for 2 months, remember, 2, you can use your x variable as 2, but then when you enter it into months squared, you have to square that 2 and enter that as a 4 in there. So be careful about that. Okay, and then here we have this in SPSS. Now, there are 2 different ways you could go about generating this output. The one that you see, this output was generated using the blocks model. So what I did is I just went to analyze and did a linear regression, and then just put it in as 3 different blocks, where block 1 just had months, block 2 had months and months squared, and block 3 had months, months squared, and months cubed. Now when you do the block model, it adds each additional variable each time. You can only use this for the polynomial transformations, because it's always going to add in all of the previous variables from the other blocks. The other option is to go through and do, under Analyze, do curve estimation, and you can select linear, quadratic, and cubic. Okay, so how do I know whether or not, this transformation was effective? You want your R squared to go up, you want your adjusted R squared to go up, and you want your standard error to go down. And we can see in both sets of output here, R squared does go up, adjusted R squared does also go up, and the standard error does go down. And so you can see that, they're listed in the same order. Now, under the model summary for the SPSS printouts, you would have to look at the significance. You can look at significance of F if you wanted in there, but you would actually have to go back into the other printouts where they show the ANOVA table in order to look at the p-value of the highest order term to make sure that that was in fact still statistically significant. But the R squared, adjusted R squared, and standard error can all be seen on here. So remember, R squared, percentage variation in the dependent variable explained by the regression. So if your regression is a better model, then your R squared should increase. Similarly for adjusted R squared. And then standard error is the amount of mistakes. The amount of mistakes should go down the better your model is. So R squared and adjusted R squared should go up, and standard error should go down. Here we look at these 3 different varieties, and we see that the quadratic relationship captures the material the best. You can also go into SPSS, and when you're doing that curved linear relationship, you can have it print out this kind of graph, which is showing you the linear, quadratic, and cubic relationships. You can also see that for the r squared there, we can see our r squareds for the three different ones coming out to see, the relationships between them. Okay, now, one of the problems, you're like, oh, this is awesome. Okay, polynomial regression, I get it. But once you have an x term and you square it, or you raise it to the third or fourth or fifth or however many powers, there's often going to introduce a problem, the multicollinearity problem. Now we know x being related to y is good, because that's good for predictive purposes. But x being related to another x, that's not so good. So anytime you add a higher order term, you're definitely introducing a potential multicollinearity problem. So what you can do is use this z transformation. Now it looks kind of complicated. So zij is equal to, so your transform variable is equal to the individual variable minus the average of that individual variable. So let's just say you're dealing with x1. You have one x. And you have 5 observations of that x. 1, 2, 3, 4, and 5. So zij is 1, zij is 1, 2, 3, 4, or 5. X bar sub I is your average of 1, 2, 3, 4, and 5, which is going to be 3. So you calculate a series of different z's. Your first z would be 1 minus 3. So your first z would be negative 2. Your second z would be 2 minus 3. So your second z would be negative 1. Your third z would be 3 minus 3, and so on and so forth. So all that is saying is use the same x and then just work down the line. So z is not just one number. It's going to be a series of numbers over the entire column. And then you would run this regression using that transformed variable, and you would square that transformed variable. So obviously this relationship is showing for a quadratic. If you were to, do a cubic, you would also include, beta 3 z to the third, and so on and so forth. All right, reciprocal regressions are going to be done when we have some sort of inverse relationship, either, 1 over x squared, some sort of thing like that. So obviously when you have the squared term, you're moving things into quadrants 1 and 2 versus 2 and 4, but, you get the basic idea. So here, x and y are inversely related, but the relationship is not linear. So the example we're going to do is looking at miles per gallon. We have 150 cars, their highway miles per gallon, and their horsepower. And we can graph out this relationship, and we see that as horsepower increases, highway miles per gallon decreases, but at a decreasing rate, such that the rate of decrease is slower for the more powerful cars. So decreasing at a decreasing rate, because the rate of decrease is slower, the rate of decrease in highway miles per gallon is slower for the cars that actually have more horsepower. So again, we start off with our scatter plot, move on to a linear regression, and from there you can do your basic interpretation. Now again, be really careful. I don't say for every 1 unit increase in horsepower, miles per gallon is expected to decrease by 0.047. No. Take that 0.047 and do 1 divided by 0.047. So for every additional horsepower, miles per gallon is predicted to decrease by 21. So that was 1 divided by 0.047. So be really careful about doing your interpretations given your, given that you've done that transformation. And again, we're going to look at the same things, r squared, adjusted r squared, standard error. So moving on, I can see the same information in SPSS, see that same relationship decreasing at a decreasing rate. And then I can go ahead and do that reciprocal transformation, look at my r squared, adjusted r squared, and standard errors, and do the same thing here again in SPSS. And I'll see now, once I've done that reciprocal transformation, in both cases, I can see much more of a linear relationship. And I'll compare my r squared, adjusted r squared, and standard errors and see that my reciprocal transformation was in fact better because r squared and adjusted r squared increased and my standard error decreased. Okay, logarithmic transformations. 3 different types we can do. We can transform just x, transform just y, or transform both. So again, the first step is going to be to go through and run your do your scatter plot and see what sort of relationship exists. So in this first example I have written here, we transform both x and y. In the second model you see on that slide, we transform just x. You can also go through and transform just y. Be really careful though, this will only work for positive values of x and y because you can't take a natural log of 0, it will be undefined. So that's something you need to be really careful about. Now, how do I know, whether a logarithmic transformation is in fact appropriate? You're going to look for clumpiness. Highly technical term right there. But remember, logarithms are showing you the rate of change of the rate of change. So by taking a logarithm, you should spread out the data because you're looking at a rate of change of a rate of change. You're looking at information that's more spread based on your units. So here we have information about GDP and the dollar amount of total imports for 25 countries. And I've just gone through and run that scatter plot with GDP as my independent variable and imports as my dependent variable. And I see most of my data seems to really be clumped around the origin. So I'm going to say this is clumpy around both x and y. And I'm going to predict that I need to go through now and transform both my independent and dependent variables. So I run my initial regression first, and here I can go through, with my standard interpretations, roughly 87% of imports is explained by variations in GDP. I have my standard error, I have my coefficients. Once I go through and do my logarithmic transformation, I see much more of a linear type relationship. It's, it's much more spread out. But if I'm looking back on here, and I can see the same thing in my SPSS, but if I look back on here, wait, isn't the second regression worse? Because I've been telling you to look at your r squared and adjusted r squared from each of your models. Well, if we look at our linear regression, our r squared is 87. If we look at our logarithmic regression, it went down to 84. Now, the standard error did in fact decrease, but, the r squared would kind of give you pause here. This is why it's going to be really important to also go through and do the actual scatter plot to confirm that you do see a relationship. So make sure you do your scatter plot for your transformed variables. Also remember to examine the residuals and make sure that there is no pattern, and you'll do that just by checking off to chart the residuals for you. Now, why specifically can't I look at r squared, adjusted r squared, and standard error when I'm doing my logarithms? Because r and f can't be compared directly, since we can't compare a logged number with an actual number, with a quote-unquote regular number. Also, you'll have to be very careful here about your interpretations. So just like you have to remember to, take the natural log of something before you put it in, you have to undo the natural log in order to do that interpretation. So you would have to take the exponential, the exp of that number. So the exponential of 0.86 is 18.29. So I wouldn't say for every 1 unit increase in GDP, imports are expected to increase by 0.87. No, I would say for every 1 unit increase in GDP, or for each additional dollar in GDP, imports are expected to increase by 18.29. Okay, so, and the way I got that was by taking that exponential. So be really careful about, when you're doing your predictions, you put a number in there, make sure you perform that transformation once you put it in, and then when you're going to do your interpretation, make sure you undo whatever that transformation was. You can, so here we see, that information again using our SPSS relationships. Okay, S-curve relationships. So what this is showing, the first model there is taking the exponential and reciprocal transformations both being involved. You can also take, a logarithm and a logarithm, undo that, if you were to go through and need to do that interpretation of t. So this is just showing you that you can, in fact, combine two or more of the transformations together if absolutely necessary. At this point, I'm just going to be happy if, you're familiar with the basics of running those transformations. And if you happen to find a paper that involves more complicated transformations, just be aware that, they can occur, and we would talk about how to input the data, how to transform the data to get it to come out the way we expect. Okay, that's it.